So am I supposed to start?
9 a.m. We're going to start our workshop. It's a good news, last day. And the first speaker, Lorenzo Toniazzi from New Zealand, University of Otago. And he's going to talk about how to formulate no-flux boundary conditions for Lévy process. So please.
Okay. Hello, everybody. Can you hear me well? Okay, let me know if let me know if there's any problem with communication. And I see you can see the slides. Awesome. Okay, so I'm going to talk about no-flux boundary conditions for one-sided Lévy processes, and it's a little bit preliminary. This is a joint work with Boris Baeumer and Mih&aacute, which already talked today, and this has been supported by the Marsden Fund of the Royal Society of New Zealand. So just let me give you a quick overview. So the idea is quite simple. So there's going to be a finite difference scheme that approximates the generator of a one-dimensional, one-sided stochastic process, which is going to be a Lévy process. And we do this to do two things at once. Once is obtain a pathwise description of a PDE, and the other side is obtain the boundary condition of this PDE. So let me put it this way. So we're going to have two types of boundary conditions. We focus on be a Neumann, so very standard or stochastic reflection will be denoted in blue. And this pathwise for the process is defined by compensating with the minimum energy of the process to keep it inside the domain. So basically, we're putting a wall at the boundary for the particle. The second boundary condition would be what we call a fast forward. We denote it in this orange, yellow thing. And this means just remove the time the process spends outside the domain. So this boundary condition means that you only observing what the process does inside the domain, and you forget about what's happening outside. And this is a bit less common, but it's still quite natural, because for example, it's the right boundary condition to study the time a certain process spends inside an interval. Because I'll explain later, when the process jumps, Neumann is might be not suitable. And anyway, so that's just a rough overview. Now just a couple of slides on what this would look like if we were dealing with a Brownian motion. If we were dealing with a Brownian motion, we have a discrete Laplacian. So this would be our finite difference scheme. And then what we would do, we will run this the corresponding random walk for a long time. And this, of course, well known. There's these two sides of the same coins. We have on one side, we can get a strong convergence of the second order operator. And on the other side, we can get a strong pathwise convergence in the sense of Dongster of the random walk to the Brownian motion. And this gives these two, on one side, the marginals of the Brownian motions, on the other side, the heat equation, and these two are equivalent. And then one can, with standard techniques, recover the path of the Brownian motion. And so the idea is that we want to achieve this equivalency, putting the boundary condition on the random walk, and then taking the limit and obtain the boundary condition in the sense of the process on one side, in the sense of the heat equation on the other side. So now that in the fractional case, this will look like the following. We have we take the Gr&uuml coefficient, and our finite difference scheme, or say continuous Markov chain generator, would be this guy here, this Gr&uuml formula. So first, notice we see that this is one-sided, right? Because we have, because the process can jump to the left only to minus h. Meanwhile, can make positive jumps of arbitrary size to the right. And this is well known. The Gr&uuml scheme approximate fractional derivative that one could say is one-sided Riesz derivative, or well, you can write in this formula where we differentiate once, integrate with respect to the one-sided kernel, then differentiate again. And right, so let's just do another graph. So this is the correspondence of what will happen here with simulated random walk based on the Gr&uuml coefficients. The second one conditional central limit theorem fails, and so when you run this for a long time, what you see is a process that now has discontinuity and can make jumps. And so that the dealing with boundary conditions becomes more complicated. And for example, one of the sort of benchmark results that we try to generalize to general one-sided processes from the fractional case is the following. So this is just what the heat equation will look like in the fractional case. This is just another way to write the previous generator on the fractional process. And so this is one of the central results they want to generalize. So here in the proof idea, we have in red the process that is free to move, the random walk. And then we apply this, we subtract the running infimum, which is a definition for stochastic reflection from the process. And this is going to converge by the continuous mapping theorem to the stochastic reflection of the stable process. This one's not stable process. And then one wants to know what the boundary condition that once applies to this PD right here at 0. Now here we're putting the boundary condition at 0. And right, and for the backward, we will have a standard Neumann condition. Meanwhile, for the forward equation or the forward Fokker-Planck equation, so the operator will be the joint operator, in the sense the jump will flip, but the boundary condition will not be a Neumann boundary condition. It would be the following Riemann-type operator. So it precisely will be a Riemann derivative of order alpha minus 1. So you lose an order of differentiation, and then you evaluate at the boundary. And this has to be this operator. It cannot be the first derivative, because the function in the domain of the generator, the first derivative will not be integral. So for the forward equation on L1, in a sense, you need to smooth out function in the domain before you can differentiate. And right, and this is quite a recent result from 2018. And it's one of the main results that we aim to generalize to one-sided processes. And right, this is just, let me check the time. This is just a quick picture. So there's going to be these two types of boundary condition we focus on. So say in red, we have the process that is free to move. In blue, we have the stochastic reflection, the process that when it tries to go below 0, we just compensate with a running infimum, so we keep it above the boundary. And you can notice visually that the process leaves the boundary continuously. Meanwhile, here in orange, we have the fast forward boundary condition. And if you notice what happens, just we removed the time the process spent below 0, and this peak right here, it moved backward at the beginning, close to the beginning. And you cannot really see the picture, but what happened there is that there's the process left discontinuously from the boundary, it jumped back inside in the domain. Right, so this is just to say, okay, Neumann and fast forward should be intuitively be different boundary conditions. And yeah. Okay, so this is just a slide repeating what I just said, and this is just how we define fast forwarding just this random time change, and then you remove the time process spent outside the domain, and should be okay. So quick summary of the main result. So it's going to be x to the psi, where psi is going to be the symbol of the process, going to be a one-sided Lévy process. And then we're going to consider free boundary conditions and all the combinations of them. D for Dirichlet, or kill the process when it leaves the domain. Neumann stochastic reflection. Fast forward, remove the time the process spends outside the domain. And I wanted to kind of, that's okay. Anyway, so we're going to put this boundary condition either on 0, on 1, on either side of the integral. And for example, here I'm saying I might put, let's make an example. So say here we say, oh, take this one-sided process and apply a boundary condition from here to the left at 0, boundary condition to the right from here at 1, and then you obtain a new Markov process. And this is equivalent to defining certain essentially backward and forward solvents, but semi-groups in terms of scale functions of these one-sided process. Now we're not focusing on scale functions, just scale functions are functions that transform to 1 over the symbol of the Lévy process, and they're very, so when you're dealing, for who doesn't know, when you're dealing with a one-sided process, these functions allow you for a very sort of explicit expression of a lot of quantities. So you sort of should use them, and so these are the natural objects to express a lot of quantities when the process is one-sided. And right, so we start with the process, we obtain semi-groups, and from the semi-groups we obtain the boundary conditions. So the thing that we are mostly interested in is that you give us an operator. So we give you the local calculus of the PDE, what's the operator, what's the boundary condition, and from that you can recover exactly what the probabilistic description of the process is behind the heat equation. In a second. Okay. So the idea of the proof, I don't think there's much time to do it, but the main idea is that it's the one I mentioned before. We had this finite difference scheme, and it converges strongly to an operator, say a continuous function for the backward. And on the other hand, we're going to have a process that converges in the Skorhole sense on the Cadillac spaces. And these equivalents will be kept through while we take the limit, and we obtain both these, basically the equivalence between 1 and 2. And right, so a little bit of setting. So x to the psi, and if, in our work, if you go, see it's going to be a one-sided. We remove the diffusion part for simplicity. We take your recurrent to not have to deal with too many cases. For example, if the process is recurrent, the process leaving the boundary by a jump is going to be equivalent to reflection, because it's going to re-enter in the same way that a reflection does. But so these are sort of minor conditions. Still, we're still treating all one-sided Lévy process. So anyway, these guys, the symbol is the following. This following Laplace transform of phi, where phi is any Lévy measure that satisfies this, plus no first moment to guarantee unbounded variation close to 0. And so this would be, say, a way to write the generator of this process on R. And we write in this Caputo, say mix Caputo way, we differentiate the function, apply the kernel capital phi, differentiate again, where capital phi is the double integration of the Lévy measure. So in the fractional case, you have 5y would be y to the -1 minus alpha. So capital phi would be y to the 1 minus alpha. And you get your sort of Riemann-Liouville calculus back. So what's our approximating process? The approximating process comes from, see, the works of Lévy from 1998, which he wants to approximate general no local differential operators, and he says, take the symbol and take 1 minus z divided h of the symbol, and then the Taylor expansion is going to give you these coefficients. And these coefficients are your standard finite difference coefficients in most cases. But then this gives you, you just put them in the same formula that we had before with Gr&uuml, and this gives you convergence in the limit. And I think this is, it is maybe easier to explain with an example. So if you had the Brownian motion, then the symbol is z squared, generated is the second derivative. So we write out what this is for z squared, and this is simply 1 over h squared minus 2 divided h squared z, and just the first free coefficient on 0, and these are the coefficients that correspond to the discrete Laplacian. Very simple. For fractional process, we have 1 z to the power of alpha, sorry, I z to the power of alpha, and you write out the Taylor expansion, and what you get is, of course, the Gr&uuml coefficient, and so you get the Gr&uuml approximation. So this is like a natural way to approximate this generator. And the nice thing is these coefficients are always all positive apart from the second. They sum up to 0, and so they allow you to construct a conservative Markov chain. And this is quite easy to show. So now I'll give you, so this is sort of the nice part of the proof. So I'll avoid discussing the complex details, how you make this work, but it just give you the idea how the boundary condition pop up, and they must be the boundary condition of the corresponding processes. So the idea is that we take this finite difference scheme, that's just a compound Poisson process, and we apply the boundary condition pathwise to the process, and then it's easy to recover what the generator of this compound Poisson process does, because it's just discrete values, very treatable. And once we know what happens to this finite difference scheme, we embed this scheme in a setting where the convergence in the Trotter-Kato sense, so the convergence of the Markov generators on continuous function L1 functions, their strong convergence there will be equivalent to the convergence of the process on the Skorhorst space. And because we have this if and only if, then when we look at what happens at the boundary, you see that the convergence, for example, for a Neumann condition for the backward equation at 0 happens, requires the convergence of this term. And because of this, the symbol 1 over h goes to 0 multiplied by h squared, while it goes to infinity for unbounded variation processes. When multiplied by h, this first difference requires that the first derivative is vanishing. And this is because P must be smooth enough so that you must have a Taylor expansion there. Can you still hear me? Because says my connection is not stable.
That's okay.
Okay. Right, and so because of this if and only if, we, in a sense, we can deduce that, okay, for backward Neumann problem for one-sided or one-sided Lévy processes, the first derivative vanishing at the boundary is the correct boundary condition. Then one can do the same for the fast forward. So you apply fast forward to the compound for some process. And this is a bit more complicated, but one can compute how it moves from the boundary. So you can obtain this expression for the generator at the boundary. And then you do some Laplace transform work, and you realize that the convergence of this condition requires that this guy converge, but this is a constant. This vanishes in h, and then we have something dependent on h divided 1 over h. So this constant here must be 0, but this constant is so this constant is our boundary condition. And what is this? This is actually has a very nice way, but very nice intuitive explanation. So this is our one could call it a reinsertion in the interior boundary condition, and this guy is differentiate once your function, then convolve with your kernel, and then an integration by parts, and you can write this in this way. And this way is saying the process, the fast forward process bounded from 0, it jumps inside the domain at y, given this weight nu, which is based on the Lévy measure right here. And so this gives the intuitive description of how the process, about the orange process jumps back inside the domain. And we knew the process will be allowed to jump back in the domain, but the key is understanding the measure that describes these jumps, and this is the correct one. And so also a quick, just a quick note: this type of boundary condition is allowed also for Brownian motion, which was found by Feller in 1952. I'm running a bit late, so let's just give this. Okay, so now I'll give you a few examples of the type of problems that we identify. So this is the whole result, if you want. So take the process, apply, say, Dirichlet on both sides. And then we say this is the PDE, the backward PDE, and this is the forward PDE on 0, 1. And what does this mean? Let's start first. Let's just do this example first. So for example, here we take one-sided Lévy process, and we apply stochastic reflection two-sided on both as 0 and 1. And this is quite a well-studied object probabilistically. And then so what we show is what is the correct Fokker-Planck equation that describes this process. And it turns out it's a Riemann-Liouville type of problem, because in the domain, you have the first derivative in time is equal to this operator, where you convolve first with your kernel, and recall capital phi in the fractional case would be y to the 1 minus alpha of the constant. You convolve with your kernel, and then you differentiate twice. Meanwhile, the boundary condition will be this 1 degree less Riemann-Liouville operator. Indeed, you see that here, the psi minus 1 derivative will be phi convolve. So your function convolve with the kernel, differentiate only once. And so it'd be a Riemann-Liouville type derivative order less than 1, then the generator. And right, and so this, if you put the fractional, of course, you get back the result that I mentioned before, right up here. It's for the boundary condition as 0. And so this table is simply saying, if you give me a Caputo generalized derivative, and you apply a Caputo of order, a Caputo type of order -1 and left and right, then the process you're describing is you're fast forwarding at 0 and you're applying Neumann at 1, or fast forward 1, that's interchangeable, etc. So we create this dictionary for what's the heat equation and what's the stochastic process. And right, so am I supposed to finish at 25 or 30 or?
Well, you've got a couple of minutes and then time for questions.
Sorry?
Couple of minutes and then time for questions.
Okay. So this is some picture. This is for how the density of for the forward equation develops for two-sided reflection. This also was a known result. This state, I think, was found by Pistorius, 2004. And this is instead what happens when you fast forward, when you remove the time the process spends outside the interval, and we get completely different steady state. You just converge to a constant with no singularities. And this, I would spare you this slide, but this is just another way of looking at that problem where we just compute the time a process spends inside the domain, given that we apply a fast forward of a Neumann, and then just the very different behavior. The expected time grows as the stability index decreases for Neumann, and it just converges to constant for fast forward. And this is all the scale functions, blah, 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 that I decided not to discuss. And yeah, so the conclusion, what's the conclusion? So the main message that we construct a first order scheme to derive in one shot boundary condition and pathwise description of the processes. And for instance, I think the main contribution is giving a way to have a no local calculus to treat this forward and backward equation in a nice way that tightly generalizes the fractional calculus results. And some of the main results would be that, for example, you have this, I didn't discuss this slide thing. And so if you have a Fokker-Planck equation for a Neumann boundary condition, you're going to expect to have this Riemann-Liouville type of derivative as a boundary condition. Meanwhile, if you're doing a fast forward, you're going to expect to have a Caputo type of no local boundary condition. So you see here the differentiation is interchanged. And well, we have some future direction we're working on. Just quickly, one, we're going to speeding up the Gr&uuml, something related to speeding up the Gr&uuml approximation we Boris, I think, talked about yesterday. We have been looking at mixed boundary conditions and also some extension to one-sided version of two-dimensional processes. And another thing that we looked at is some regularity scale functions, which is a topic that was quite active, I think 10 to 5 years ago. Anyway, yeah, that's also for who's going to get slides. I'll have some relevant references, and yeah, that's all. Thank you.
Okay, thank you, Lorenzo, for interesting talk. Well, we have a couple of minutes for short questions. Actually, as a chairman, I've got a comment regarding in the beginning of your talk, you presented a very nice illustration of convergence. And I think that the way we need to teach our students of convergence of random walk to the process, really beautiful. Thank you for that.
Thank you.
I'm going to steal this for my lectures.
Yeah, no problem.
So, any questions? Quite complicated problem, stochastic reflection for Lévy process.
I remember Vasily. I think when I started my PhD, Vasily had done some work for the case of where the process is not a bounded variation, and he told me, "Okay, go prove the unbounded variation version." And it was so hard. It was a desperate 6 months, and then luckily I gave up at the time. Do you remember the student?
Okay, thank you again, Lorenzo.
Okay, no problem. Yeah. Yeah, have a good day.
Okay.